Hi everyone, let me start by giving an overview of our project. The research question for the project is, to what extent are walkability and park access associated with cardiovascular mortality across U.S. cities under different socioeconomic contexts? Based on prior work, we expected that cities with higher walkability and better access to parks would generally show lower cardiovascular mortality. To investigate this, we used six publicly available datasets, each reporting on estimated metric. Cardiovascular mortality is provided as an estimated death rate. Park access estimates the percentage of residents living near a park. Walkability is given as a score, and diversity, segregation, and income are each reported as estimated demographic or economic values.
Okay, so let's start off with some EDA. So we first plotted a scatter matrix just so we can see the relation between our predictors and the response, and it's these five up here. And what we actually see is that there's no apparent curvature. Instead, we have a monotonic relationship with a very shallow slope. This tells us that that multiple linear regression is a viable model, and it's good because our research question is about inference. We want to be able to interpret the relationship between the predictors and the response. After we plotted the distribution um, of the response and predictors. And focusing on just the response, what we see is that we have a very large right tail. This will tell us most likely that we want to log transform our response. And then looking at the distribution of the predictors, we actually see that they all look quite different and they're scaled very differently. This will lead us to standardize our predictors, especially since we want to be able to effectively interpret their partial effect onto the response. Next, we plotted a heat map of their correlation, and what was actually alarming was that we see high correlation between two very important predictors, the park access and walkability. But to further explore this, we computed their VIF scores. So we see that park access, walkability, and diversity have high VIF scores. We definitely will drop diversity since it's highly correlated with multiple predictors, but we choose to keep park access and walkability because they are essential to our research question. Their VIF values are high but not catastrophic, and we are still able to interpret their partial effects. They also represent different aspects of city design. Park access represents green space availability, and walkability represents the built environment and pedestrian infrastructure. So the modeling process. First, we log transform our response and standardize the predictors. We then fit the model, and then after we run diagnostics on the residuals of the model to see how trustworthy and stable our model is. We also do the additional step of comparing the full model with reduced models. So a key part of that I want to highlight that's very important to our research question is how we interpret the partial effects. So let's focus on park access. We have park access, the coefficient of negative 0.0379, and its p-value is smaller than 0.05, which tells us that it's a significant predictor. And how we would interpret this, especially since we log transformed our response and also standardized, is a little bit confusing. But how it would be is that a one standard deviation increase in park access is associated with a 3.7% decrease in cardiovascular mortality, holding all other predictors fixed. It's important that every time we interpret each predictor by their coefficients, we always mention holding all other predictors fixed, since what we are interpreting is a partial effect. So we see that park access and income are statistically significant, while walkability and segregation are not.
And now I'd like to conclude with a wrap up of all of our results. Overall, our analysis reveals that while walkability and park access appear superficially similar and are moderately correlated, they play distinctly different roles in explaining cardiovascular mortality when socioeconomic context is taken into account. Park access demonstrates a consistently protective association across all models, remaining statistically significant, stable in magnitude, and directionally negative whether examined alone, alongside walkability, or within the full socioeconomic model. Walkability, however, shows no robust independent relationship. It is essentially uninformative when modeled alone and becomes unstable and even sign reversing once we adjust for park access, suggesting its apparent effect is largely confounded by the availability of green space. The dramatic increase in explanatory power only after adding income and segregation highlights that built environment features by themselves explain almost none of the variation in cardiovascular mortality, while socioeconomic conditions capture substantial structural determinants of health. Despite the moderately high VIF between park access and walkability, multicollinearity did not meaningfully distort our coefficients or impede interpretation. Taken together, these results suggest that access to parks, not general walkability, is the more reliable environmental predictor of reduced cardiovascular mortality, and that socioeconomic inequalities remain the dominant contextual factors shaping population health across U.S. cities.